Hi everybody. In this video we're going to take a look at an example involving Simpson's 1/3 rule. So if you recall, this is Simpson's 1/3 rule right here. So what we're doing is we're approximating the integral from a to b, f of x dx, with this sum of linear combinations of the function evaluated at certain nodal values. And also, if you recall, we have an error bound for Simpson's rule given by this quantity right here, h to the fourth divided by 180 times b minus a times m, where m is a bound on the absolute value of the fourth derivative of f. Now, also recall that this summation right here can also be written like this. We can write it as h over 3 times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3, and that pattern continues, and then we end with 2 times f of x sub n minus 2 plus 4 times f of x sub n minus 1 plus f of xn. So you have this pattern: 1, 4, 2, 4, 2, 4, 2, 4, 1 is what you end with. And because of this pattern, the n up here must be an even number. If it's not an even number, then you would have to, perhaps you could use Simpson's rule on the nodes from x0 to xn minus 1, and then use the trapezoidal rule from xn minus 1 to xn. There are ways around that, but when we're applying Simpson's rule, we're going to assume that the n is even. So let's take a look at this example down here. So let's use Simpson's rule to approximate the integral from 1 to 2 of 1 over x dx using 8, with n equaling 8. So actually we would have 9 total nodes. With the n being 8 up here, if we start at x0 and go through x8, then we would actually have 9 nodes. So it gets a little confusing there. You have to remember, for Simpson's rule, the n must be even when you go x0 to xn. But then that actually means you have an odd number of nodes. Okay, so the n is even, but you have an odd number of nodes. Alright, so we're going to use Simpson's rule to approximate this definite integral down here, and then we're going to compare the actual error to this error bound. So we'll calculate this error bound, and we'll see that our actual error is smaller than that. So with n equaling 8, or 9 nodes, let's set up our picture here, what we're going to do. So we're going to start out with 1, and that's going to be our x0. x0 is a. And then we're going to go out to where x8, that's going to be 2. And then we have our other nodes that look like this. So this is going to be x1. And now let's see, what is the distance in between each of these nodes? That's h. Alright, so now the h in this case, h is always b minus a over n. So in this case, that's going to be, of course, 2 minus 1 over 8. So that's going to be 1/8, right? So if this is 1, this x1 is going to be 1 plus 1/8, or 9/8. And then x2 is going to be 10/8, and so on. And then 2, of course, is 16/8. Now, all we have to do is apply this rule right here, and so what we get is our integral. Alright, and so there you have it. So what we have to do is evaluate this now. So that right-hand side is going to equal and there you go. You notice that each of these terms, like 8 over 9 and 8 over 10, those are f of 9/8. Right? The reason they flip, of course, is because the function f that we're using here is 1 over x, right? You know, f of x is 1 over x in this case. So in this particular example, that's why we just flip them. That, of course, is not going to be the case for other functions that you might approximate using Simpson's rule. Now, when we evaluate this, so when you evaluate this, you can use your calculator or Excel. I will show you in a second how to do this with Excel. What you get is 0. So that's what you get when you evaluate that on your calculator. Now, let's evaluate an error bound, and then we'll calculate the difference between the actual error and our estimate right here, and show that that is less than our error bound. So our error bound, let's first of all calculate the m right here. So the m is supposed to be a bound on the fourth derivative of f. So we have to evaluate that fourth derivative. Well, let's just do that up here. So first derivative, of course. Second derivative. Third derivative. And fourth derivative. Alright, so our fourth derivative being 24 over x to the fifth, what that means then is our m, we have to find out where this has a maximum value between 1 and 2. Alright, so to make this as large as possible, the 24 over x to the fifth, we want to make the denominator as small as possible. So the denominator will be smallest when x is equal to 1. So our m is going to be 24 over 1 to the fifth in this case, and so of course that's just 24. So that's what we're going to use for our m, and so therefore our error bound will be h to the fourth. Now the h in this case was a 1/8, right? So it's going to be 1/8 to the fourth divided by 180 times b minus a is 1 times m, which is 24. And evaluating this, we get 0.0000325. Alright, so that's our error bound. Now let's check our actual error that we incurred in this with this approximation down here. So our actual error. Alright, now of course the integral, we have to find out what is our actual value for that definite integral. Well, of course, integral from 1 to 2. This is natural log absolute value x evaluated from 1 to 2, which of course is just the natural log of 2. So that's actually what this definite integral is. It's the natural log of 2. So if we look at our actual error being the absolute value of the ln of 2 minus this number down here, and I'll just write that as 0.6913. I'll just write it like that. When we evaluate that, we get 0. And we actually get 7.35 times 10 to the negative 6th. Let me just write it like this. Which is basically you have 5 zeros and 735. So, which comparing these two, this is our error bound right here, and it is indeed larger than our actual error, which is good because that's exactly what we should have. So we verified that this value down here for this particular example, this error bound, does indeed bound the actual error. Our actual error is a little smaller than this number. This is the worst case scenario that you could have for your error. And we see that our actual error is less than that number, as it should be. Now, let me show you how to calculate Simpson's rule using Excel. And we'll get these same numbers right here when we do this with Excel. So here we have a spreadsheet set up, and I'll show you how to calculate the Simpson's approximation using these spreadsheet values. So just create a column right here with our nodal values. So you notice here we have 1. This is 1 1/8, or the 9/8, 10/8, 1.25, 11/8, and so on, all the way down to 16/8, which is 2. And the way you can create that quickly is you just put your first value here, and you see what I typed in here was just E3, which is where the A is located, plus 1/8, like that. And then you can just, here I'll show you, you can just grab this value and drag it down. And there you go, you have all your nodal values. Now over here, we have all of our function values in this column. So notice that what I typed into cell F3 here was 1 divided by E3. So that's F of 1 right here. And then you can just grab that value, grab the fill handle right there, drag it down, and it will copy all of your function values into this column. All right. Now, what we have over here in column G, let's take a look at that. So, if you look at this value, what I typed in was F3 plus 4 times F4, what's in cell F4, plus the value in cell F5. So in other words, this is this value right here. What we have right here, this is f of x1, f of x0 plus 4f of x1 plus f of x2. And then what we're going to do is we're going to drag that down, so you'll see this next value here, what we have in this cell, is then going to be f of x2 plus 4 f of x3 plus f of x4. And so you see we have an f of x2 and another f of x2. These are giving us 2 f of x2s that we're recovering in the Simpson's rule pattern. Remember, 4, 2, 4, 2, and so on. And you start with a 1. 1, 4, 2, 4, 2, 4, and end with a 1. All right. And so let's see how this works. All right, so you see in this cell right here, notice I'm notice where I place it, that's very important. It's being placed in cell G5, right aside of cell F5. So right here we have our three function values, our first three function values. And in cell G5 we have F3 plus 4F4 plus F5. Now you need a space in between these here. So what you do when you copy this down, highlight the two cells like that and then just drag down. Here, before I do that, let me delete these values just to show you that's what you get, that this will all work out. So I highlight those two cells and then I just drag down and release, and there you go. Now what we have to do is add all of these up and multiply by h over 3, and that's what we have right down here. So you see right here that 1 over 24, that is h over 3 times, and then I sum up all of these values here. So that's this sum right here. The sum, that's literally the summation in the Simpson's rule. And the 1 over 24 right here, I had to type that in by hand. That's the h over 3. And when we evaluate that, we see that we get exactly what we had before by using our calculator. And we see we get 0.693154531, which is exactly what we got before. And you know, if you're using Excel and you want more accuracy here, you can just format the cells to have more decimal places, so you can have up to, you know, many decimal places. Then I have to widen my column, you know, so there I have a few more decimal places. And so there you go. That's how you can do the Simpson's rule using function calls in an Excel spreadsheet. And by the way, over here you see we have the same thing for the trapezoidal rule. So there's our trapezoidal approximation, which is not quite as good as the Simpson's 1/3 rule approximation is, of course. And that's because the trapezoidal rule, if you look at the error bound, that incorporates an h squared, which in comparison to the Simpson's rule has an h to the 4th in its error bound. And you know, for h a small number, h to the 4th is going to be much smaller than h squared. So that's why Simpson's rule is so much better. And that completes this example of the Simpson's rule.